I'm Barbara Henley, council member representing the Princess Anne District. On behalf of the mayor and the city council, I welcome you all here tonight to hear how forests in Virginia Beach can play a role in our flood prevention strategy. I want to give you some insight into how we came to be looking at this possibility. This work grew out of a plan that was done a few years ago, which recognized the connections that our waterways provide for us with our neighbors to the south. We were particularly looking at the North Landing River. That project was the Green Sea Plan. This ended up being a cooperative plan involving Virginia Beach and Chesapeake and Currituck County. Among the recommendations was a suggestion that research include works being done by municipalities, agencies, and academic institutions which would broaden the knowledge and understanding of the total Albemarle watershed. Also a partner in that work was the Nature Conservancy, which is one of the largest landowners along the Green Sea waterways. As we realize the position that Virginia Beach plays at the headwaters of the Albemarle watershed, we propose that we reach out to others to see if there could be that collaboration among researchers throughout the area. We tested the waters in the summer of 2017 with a mini symposium which we called Creating a Shared Vision for the Albemarle. We presented the possibilities of a partnership to a group of possible participants among academic institutions and other stakeholders. With all of us looking at the looming problems presented by sea level rise, climate changes, and recurrent flooding, it became obvious that there would be much to gain if we could work together to share knowledge and understanding of these issues. We moved forward then to assemble a much broader range of topics and participants, and in April, we sponsored the 2018 North Landing River Albemarle Sound Estuarine Symposium, Building a Shared Vision. With about 35 speakers and 175 attendees, we recognize the extent of the possibilities that this partnership can provide as we try to explore all the myriad of issues that come together in this vast Albemarle, Pamlico Sound, North Landing River Back Bay system. And all of this is just so greatly going to impact our counties and cities in the years to come. One of the topics explored at that symposium was the state of the forest in the Albemarle watershed, presented by Brian Van Eerden, director of the Virginia Pinelands program for the Nature Conservancy. I stress that this was just one of the many very important aspects of the sea level rise flooding question that's being explored. But it was one that was selected for some more specific exploration at our follow-up series of topics presentations that we did last summer. At our July session, Brian again was a presenter, and the presentation was narrowed to the state of the forest in Virginia Beach. As we looked further at the very fortunate state that we find that we have with our forests, we began to question how we could take advantage of this great asset that we have and make it even better. We realized that we needed to base anything going forward on the very best science available, and we looked to the research being done at Virginia Tech for assistance. You need to hear the best information from the experts. So we're going to move from my very basic layperson knowledge to the folks who can explain that science. I just want to express my great appreciation to all of the people who have been participants so far in this fascinating project that we find ourselves participating in. The questions are extremely far-reaching, and the issues are complicated. The factors which demand exploration seem endless. I can only say that we need to keep moving forward, to explore every angle that we can find, to be open to learning everything that we can possibly learn, and above all, to be committed to working together to find the best ways that we can work through these issues that are facing us. We won't find all of the solutions next week, and we won't get all of the answers right the first time. We've got a lot of challenges, but we also have opportunities. This topic that we will explore tonight is one that has some very exciting possibilities, and it's a very good early step in our journey of exploration. Our next presenter will be Brian Van Eerden. Brian is the director of the Nature Conservancy's Virginia Pinelands program, and in that role he manages the Conservancy's land acquisition and forest management projects across southeastern Virginia. Brian has over 20 years of experience in ecological management of forest systems of southeastern United States. He received his master's degree in botany from the University of Georgia, as well as an undergraduate degree in plant science from Pennsylvania State University. So again, we welcome Brian Van Eerden.
Thank you, Mrs. Henley, and thank you all for coming out tonight. This is a wonderful show of interest for the forests of Virginia Beach. As Mrs. Henley mentioned, I am with the Nature Conservancy, and I oversee our work, forest conservation work primarily in Southeast Virginia. And the Nature Conservancy is a global nonprofit, and for the last 30 years we have been protecting natural areas in the southern part of Virginia Beach, and right now we own 3,700 acres along the North Landing River, which is one of the most biologically diverse forest and wetland systems in eastern Virginia. And the land that we own is just a small piece of the forest network here in Virginia Beach. And what I want to do is just spend a couple of minutes to talk about that forest network, provide some highlights and context for the main talk that you're going to hear tonight by Daniel McLaughlin on forest hydrology. So let's start with some numbers. Virginia Beach is an incredibly green city. Roughly 38% of the land area in Virginia Beach has a tree on it. So the tree canopy coverage is 38%. This is a land cover map showing the different land cover types. In green is tree cover. And some of the most prominent natural landmarks of the city are forest blocks. So the maritime forests along the coast, First Landing State Park, Falls Cape State Park. Inland, you have big forest blocks along the North Landing River, West Neck Creek, and also in the more mature, older neighborhoods, Lynn Haven River watershed, a lot of forest cover there. And also part of the rural character for southern Virginia Beach are all the different forest blocks mixed with agricultural land. Remarkably, 50% of that forest cover is under conservation ownership. And the fate of that forest that's under conservation ownership is largely going to be managed for long term, for old growth. Very little merchantable timber or forest harvesting will occur on those lands. And that level of forest protection really anywhere is a remarkable accomplishment. And here are the entities that control that land. So we have local parks that the city of Virginia Beach has acquired over the last several decades. The Nature Conservancy, we own a lot of land right here on the North Landing River, our 3,700 acres in dark green. These tracts in orange, those are state-owned properties. There's the Virginia Department of Conservation and Recreation, the North Landing River Natural Area Preserve. The Game Department has a Princess Anne Wildlife Management Area over here as well, and then this is Falls Cape State Park. A lot of ownership by Fish and Wildlife Service, of course, Back Bay Wildlife Refuge, and then just an amazingly successful program, the Agricultural Reserve Program here in purple. So a wide collection of a lot of conservation actors coming together to protect a lot of forest land and also some marshland. Now these forests provide all kinds of functions and benefits. For the Nature Conservancy, we first came to this area because of the biodiversity significance, but there are a lot of other attributes to forests that are important: water quality protection, recreation, aesthetics, carbon storage, and timber and forest products. And tonight we're going to hear about another very important service that forests provide, and that is flood risk reduction. The city right now is trying to find any and all solutions to address coastal flooding right now, and looking forward with sea level rise on the horizon. Sea level is rising now, but there's going to be more water, of course, in 30 and 50 years and beyond. And conserving forest land is one of several strategies that's in the bucket of what we call nature-based solutions. So there are a number of ways to use natural systems to reduce flood risk or to minimize flood issues. And so forest conservation and restoration is one of those. Marsh restoration and enhancement, oyster reef restoration, living shorelines, and also submerged aquatic vegetation restoration, particularly in Back Bay. And these strategies are meant to complement the engineering solutions that are going to be put forward by the city to come up with a comprehensive plan to deal with flooding issues. Over the last year, really led by Mrs. Henley, who was just such a champion for so many things in the city, but particularly for conserving the natural areas in the southern part of the city, a group has come together with a common interest in conserving forest land primarily for reducing the risk of flooding across the city. And so there, on the bottom of the screen, you can see all the different partners that have been assembled. And the idea is, our vision is for forest land to become integrated as a component of the stormwater management framework that the city uses to address flooding issues. So native forest conservation and restoration, we want to see that integrated into the stormwater management strategies on public and private land. So really embracing our forests as part of the green infrastructure that the city has. Our group understands that to move this very somewhat basic concept that trees are good for minimizing runoff and for flood storage, we need to have good science to inform the kinds of responses that we're going to have to conserve forest land or restore forest land. We need the data to back that claim up. And we're very fortunate that one of the cooperators, one of our partners in this working group is Virginia Tech. Daniel McLaughlin, who will be presenting here shortly, is a leader in forest hydrology. And what he is learning and the tools that he's developing here will provide the city and other practitioners, Nature Conservancy, public agencies, a way to prioritize how and where we should invest our dollars to accomplish the greatest outcome for forest conservation and flood risk reduction. So Daniel is an assistant professor in the Department of Forest Resources and Environmental Conservation at Virginia Tech. His research broadly focuses on informing water resource management through a better understanding of drivers of ecosystem function. Specific research and teaching interests include forest ecohydrology, wetland and stream processes, emerging environmental sensors, watershed hydrology, and biogeomorphology. Daniel has a PhD in systems ecology and ecological engineering from the University of Florida, a master's in environmental engineering from Clemson University, and a BS in civil engineering from Clemson University. Please join me in welcoming Daniel for his presentation.
Well, thank you, Brian, and thank you, Mrs. Henley, and thank you all for being here. I'm excited to be here today and excited to be part of this group, which Brian has already kind of introduced, this very much collaborative group and coupled research to inform forest management and forest conservation for urban flood reduction. And we're going to get into the nuts and bolts of that and that specific research that we're leading to kind of inform those efforts. But first I want to kind of paint the picture of forest in general, background of forest, what they are, and particularly the interactions between forest and water. As Brian said, I'm an assistant professor in the Department of Forest Resource and Environmental Conservation. My research spans headwater streams, or our research, it's a group effort for sure, headwater streams, forested peatlands, including the Great Dismal Swamp, as well as places up in northern Minnesota and into Florida, and wetland systems as well. But while those systems are different, those ecosystems are different, and places are different, and scopes and questions are different, our research really tries to focus on the interactions between ecosystems and water, and what that means for specific ecosystem functions that we benefit from. And that's water quality, water quantity in this case, but habitat, and the list goes on. And so that kind of framework kind of guides our research efforts and is part of the topic today. So again, I want to kind of paint the picture of what forest in general first before we kind of move into the nuts and bolts of the topic at hand. And I also actually want to, before we even get there, kind of spin it in a different way and talk about forest management in places where we want more water. And so I'll provide a case study for that, which will be a nice segue into places like Virginia Beach, where we want to use forest for less water. So here's our general outline, which I more or less just said, a little background of forest and how they interact with water. Then we'll go into that case study, a couple of slides in terms of forest management for more water. And then we'll get into really what you guys are here for today, which is urban forest for less water, and then some specific research that we're leading to inform urban forest conservation, which is more or less the right photo for flood protection in urban systems. So we'll start here. And we'll start by looking at, well, you know, I can show you a couple of pictures, and I will, but you guys know from your own experiences and your own travels that forests look different, right? So here's a beautiful shot, and it's hard to see with the lights, of the Osceola National Forest in North Florida, right? A longleaf pine stand there. Here's Jake Diamond, a PhD student of mine, in the black ash stands of northern Minnesota. Quite different. Here's Gracie Irwin, a master's student of mine working in systems close to home in Blacksburg, these Appalachian systems and the headwater streams that drain those systems. And then closer to here is Morgan Schulte, my first master's student actually, who is now at NC State, and she did her master's work in the Great Dismal Swamp, a forested peatland. So these forests look quite different in terms of their soils, the canopy, the climate, and the substrates. But I would argue that all forests actually look the same in terms of the compartments and their processes, right? So they all have trees, which is obvious. But those trees can be different in terms of their composition, the type of species that they have, right? They can be different in terms of the canopy cover, from full canopy cover to thin and everywhere in between. Then we also have shrubs and ground cover. In this system, in the Osceola National Forest, you can see there's not many shrubs in this case. Again, hard to see with the lights, but there's plenty of saw palmetto in terms of that understory and that ground cover. And again, the amount of shrubs and the type of shrubs and ground covers varies by climate regime, soils, and also what's on top in terms of available sunlight. And another key compartment is what's on the forest floor and subsurface in the soils, and that's storages of nutrients and waters and the bacteria that kind of cycle and process those things along with organic matter, right? But then, of course, there's weather and climate on top, where we have precipitation providing that water, and then we have the sunlight providing the energy to fuel photosynthetic activity, or tree and biomass, plant biomass growth, the trees and those understories. So that fuels this right hour, right, to take up that stuff to support that forest growth. And of course, the forest delivers stuff back to the soil in terms of litter fall and sticks and whatnot. And that's processed by the microbes. So there's some internal cycling here. But if we focus just on the water, there's a cycle between the climate and that forest. Of course, is providing the precipitation and that solar radiation, right? But this is pulling a lot of water to the tree canopy and those shrubs and ground cover, which is fueling photosynthetic activity. But only about 6% of the water that a tree takes up becomes new plant biomass. The remainder, that 94%, goes back to the atmosphere. And so there's that cycle between a forest and the climate on top. Now, and through those processes, right, and Brian did a good job already mentioning these ecosystem services that forests provide, from carbon sequestration, that's pulling in that CO2 and live biomass and that organic matter on the forest floor. Habitat, people like to walk in those forests. We can use that carbon sequestration for biofuels or timber. There's food sources, wildlife, and wood, which is a big one, of course. But today we're focused on what they mean for water. And they can be, which will be the subject of the end of the talk, flood control, and our focus here, but it also can be for water supply as well. So if we kind of zoom in on the forest and water interactions, and I like this picture, it's a picture from a pond stand in Waverly, Virginia, because you can see it's storing water. And that is that forests capture, store, and use water. And I don't want to focus just on trees today. I want to focus on all the attributes of a forest that regulate water cycles and water storage, regardless if you're adjacent to an urban system or if you're out in the middle of nowhere, right? We're just talking about forests and how they interact with water. And again, it's not just the trees, it's a variety of attributes of a particular forest that enable them to capture, store, and subsequently use water, and what that means for a larger landscape in terms of water storage and provision of water. So let's make it, let's put it in a cartoon perspective and think about first that capture and storage. Okay, so that's what we're looking at here, where we have the storages, and there's kind of three compartments. There's interception, surface storage, and soil infiltration. So interception are the umbrellas in the system. I'm showing it here with trees and the drops of water on those trees, but I could put in those shrubs, I could put in that saw palmetto, and even there's ground cover and grasses that provide interception. They capture that water. Okay, and the remainder of that water then falls to the forest floor. But that can capture a lot of water during an individual storm event. Now, the remainder of that water then becomes either surface water storage or infiltrates in the ground or leaves the system. So what falls from the atmosphere minus what is stored in that system across these three components leaves the system. It either leaves it groundwater flows subsurfacely, or again, the topic of today we'll get to is overland flow or runoff. All right? So the storage matters immensely in terms of what leaves this system. Okay, and that storage I've already mentioned is interception. Now what's left either can, in terms of getting stored, can become in terms of surface water storage. These forests aren't flat. They have undulating surfaces, and that varies across different forests. And these depressions can be small to big, and they're likely most often manifest as wetland ecosystems, right, where they store surface water. And that's determined largely by topography, of course. Now, the water can also infiltrate into the ground, infiltration, and that becomes, it can become soil water, or it can go down to the saturated zone or the groundwater aquifer or the water table, however you want to couch it. Now, so that's important. That's how they store water. They capture and store that water, and the remainder of that leaves this block, leaves this cartoon in a variety of different ways. But how much they store determines the remainder of that precipitation event that leaves the system. Now, a very key part of that is the replenishment of that storage capacity, that ability to store water between storm events. And that's where we get into the term evapotranspiration, or I'll use it quite often, ET. So evapotranspiration, there's really two parts to that. There's the evapo part and there's the transpiration part. So plant water use, be it a tree, be it a saw palmetto, be it a blade of grass, be it a tomato plant in your yard, when they use water, they pull that water up. They do that to have a vector for nutrients they need. A little bit of that becomes plant biomass in that photosynthetic reaction. But again, most of that, over 90%, leaves. And they do that to cool themselves so they don't go wilting, just like you perspire when you take a run. It cools that leaf surface so they do not wilt. So that's the major function of that water use, in addition to bringing the nutrients up. All right? But there's also another component of that evapotranspiration. That's the first part, and that's evapo. And that's both open water evaporation and evaporation of soil water, just like the reason you're not supposed to water your grass in the middle of the day, not because the grass blades are going to use it, because that's what you want. It's because a lot of that water in the soil pores is going to evaporate because it's too hot and you're watering in the middle of the day. All right? And so that collective term will reduce what was up here in this terms of this dotted line, will reduce that water table and soil moisture to some lower level, and it will decrease what was this standing water to some lower level, thereby replenishing the surface water storage, the soil water storage capacity of this particular forested block for the next round. Now, I want to go through each of these kind of components briefly, again, given the nuts and bolts of how a forest and water work, before we can get into the context of forests for flood protection. So I'll start with water capture and storage. I got some eye candy up here. I didn't take that picture, but it just shows you, as you all know, and you all kind of go under a tree when it's raining, right, so you don't get as wet, that leaves capture water, right, and that's what we're showing here. Now, you can imagine that's a pretty hard term or number to get at, because depending on which way the wind blows or what side of the tree you're on or what tree you're under, right? It's quite variable across storm events and under a forested stand. So it's a really hard number to get at, and a lot of people have dedicated careers at getting this number. We've kind of gotten a little creative with it in Florida to get at it by saying we want to have the integrated or the aggregate kind of interception across the top of the canopy through that ground or the bottom of that forest floor. And we put a soil moisture sensor, a simple sensor that tells you what the soil moisture is. In this case, we'll just say it tells you when it changes its wetness, when there feels a wetting event from a storm event, when that soil gets wetter. And we just track the rain amount that it takes to make that sensor wet. So if it took a 1/4 of an inch to make that sensor wet, that means that interception storage was a 1/4 of an inch. We had to store a 1/4 of an inch of rainfall, and then the next little bit of rainfall then wetted our sensor. And so we've done that across forested stands in Florida. I'm showing 6 here. This is only one of 2 graphs, I promise. And on the bottom x-axis, this horizontal axis is leaf area. There's various different ways of measurement. We don't need to get into that today. It's just how many leaves are in the system. And on the y-axis, this vertical axis, is the amount of water that was stored before our sensor got wet relative to the total amount of rainfall in a given year. So we did this over a whole year. How much did the forest hold in terms of interception relative to how much rainfall that particular forest got? And it's not surprising, the more leaves you have, the more umbrellas you have, and the more water you can store. The reason I bring this up is not to show that we can populate this relationship, but note these numbers. That's 16 to 21% of annual rainfall can be stored in tree canopies and understory canopies. So that's a big number that we need to be thinking about, and a big role of forest in terms of capturing that water. Another one is surface water storage, right? This is in southeast Virginia, I think, again, near Waverly. This is a mixed forested system, swamp system in Florida. And the point is, there's a lot of these depressional wetland systems that are embedded in an otherwise forested system. And they can be small to big, but they're there particularly in flat landscapes where a little bit of relief, a little bit of depression can hold water, like the coastal plain, like Virginia Beach. And again, it might be hard to see, but we can look at them from Google Earth, and we can look at them in mixed land uses, and we can see them. There's a golf course, so there's going to be some there. And so there's some artificial ones, but there's some natural ones, and even if you had a computer in front of you, you might think that was one just because of different shading, but it's hard to see under the canopy. And what we're talking about, and what we're going to try to get to towards the end of the day, is an ability to look at these various different components across the whole boundaries of Virginia Beach. We can't do that on the ground, right? We need to do that from available data, wall to wall in terms of geospatial data. And so we need an ability to look under the tree canopy, but not with individuals. And now we have new technology. Maybe some of you have heard of LiDAR, but it's this remote sensing technology to get highly accurate topographic maps. Incredibly accurate topographic maps. These data are becoming more and more publicly available from our federal agencies that are providing these data. And you can see here, it picks up buildings and tree cover as well, which we're finding, particularly the tree cover, very useful. But we can take away that, and we can also look at the undulating surface in terms of topography, and we can look at these depressional systems. We still need a way of using those data to quantify or identify individual depressional features that can hold water, and to quantify how much they can, because they're not all the same. So in some work that we've done close to here, but in the Delmarva Peninsula, here's a particular just one watershed in the Delmarva Peninsula. This is the Greensboro watershed, if you're familiar with that area. It's a really wetland-rich location. It's a lot of depressionals. Maybe some of you have heard of Delmarva Bays. We've taken that available topographic data and developed new processing methodologies to take those data and to identify each individual depression, which is outlined in the orange, and then we can really look at it in 3D and how much water each of those depressions can hold, how much each of those buckets can hold before they spill over, right? And that's their storage capacity. Of course, the water can go into the ground in terms of infiltration. And just really quickly, you can just think of this as a jar with marbles in it, right? And you start dumping water in it, and how this pore space, the space between the marbles, determines how much water that jar can hold, which is going to be a lot less water than an empty jar would hold, right? You put marbles in it, can hold less, because now all you have to work with is the pores in between. Those soil particles are those marbles. And you start filling it up, and it fills from the bottom up, right? Well, not all marbles are the same in this analogy, and not all soil particles are the same. So we need to know something about different soil types. We have soils that are like this. We have soils that are like this, right? And everywhere in between, right? And they have different abilities to let water permeate through them and how much water they can store in their pore space. So that's another thing that's widely variable across regions, but even within regions like Virginia Beach in terms of soil type and what they can do in terms of infiltration. Now, the other part of that, in addition to soil type, is how tall is your jar, right? Now, how much water do you already have in your jar is another way of thinking about it. So here is just a cartoon to show you this green is an undulating soil surface, and here is the top of the water table or the aquifer. If you dug a hole in the ground and you let it fill up, that's where the water would come up to. Okay? Here's a tall jar, here's a short jar. Same soil types across this cartoon. This location is not going to be able to hold and store and handle as much infiltrating water before the water comes to the surface as this would. Highlighting that to understand and to quantify soil water storage requires understanding the soil types, but also the depth to water table. That's the storage part. Again, 3 components, and just kind of giving you some overviews of the things that we need to think about in terms of those components, and highlighting that they vary across forest because of forest attributes, leaf area, and kind of substrate or soil attributes, and subsurface in terms of depth to water table. Something else that varies across forest systems is that key loss term, and this is a very important part of what forests do. And how they regulate the water cycle on the ground, and again, their feedback to the atmosphere and the climate system. This is this evapotranspiration. I've already kind of walked through the 3 components of that, but I'll remind you here. Transpiration from trees and anything else green in the system. Soil water evaporation, that's that soil water that's now in these pores. If I wanted to bring that image back up, that's in that jar of marbles. Some of that can evaporate off. And then we have those wetland systems holding water that we can quantify how much water they can hold, but then they're going to subsequently release water via open water evaporation. Of course, we can have trees in our wetlands too, so now you'd have transpiration and open water evaporation. And it's really hard to parse these different flows, so we just combine them to be evapotranspiration. All right? And that's a key part because it lowers the storage, the existing storage, increasing storage capacity. Now, this water flow back to the atmosphere can be quite large or can be quite small depending on time of year. My guess is it's quite low today, but it can be quite high in the middle of the summer in Virginia Beach. Places out like on the northwest of the United States is always low. So it varies by region and it varies by season. First of all, by climate, which should be obvious, right? You need wind, you need low evaporation, and you need solar radiation and temperature to fuel this process. But it can be quite big. It can be up to 1/4 inch a day in the summer. Now, you put that in the context of a storm event we have today. I'm not sure how much we have today, but let's throw out a 3-inch rain event. You're like, well, that doesn't mean much. 1/4 inch of that 3-inch rain event. But this 1/4 inch can happen every day. That 3-inch of rain, and even any rain event doesn't happen every day, unless, again, you're out in the northwest. So thinking about the cumulative amount of this flow over a year. And indeed, that flow, cumulative, relative to how much rainfall a system gets in any given year can be quite big. So around here, maybe we can lose 50 to 80% of the incoming rainfall back to the atmosphere, right? And that's something we call water yield. Precipitation, what comes from the atmosphere minus what goes back to the atmosphere, is what's left over to become soil water, to become surface water, to become down gradient water in terms of runoff. That is the water yield of the system, and that's a key part of today's talk. If we look across regions, there's me pointing to the northwest, we're over here. The hot colors mean you're evapotranspiring a lot more relative to rain, with these orange colors meaning that you're pretty much losing every bit of raindrop that you have back to the evapotranspiration. That's why it's incredibly dry out there, right? Whereas in these cases up here, where it's extremely wet, is not just wet because they get a lot of rainfall. It's wet because they get a lot of rainfall and hardly any evapotranspiration. And evapotranspiration is 0.2 to 0.3, these purple colors. Only 30%, let's say, of the incoming rainfall precipitation goes back to the atmosphere, meaning that 70% of whatever that rainfall stays around. Right? Now, we're over here. And depending on where you are and if you can squint, maybe we're 50 to maybe 80%. We've done work in Florida to show that there are stands that are 90% and systems that are 90%. But that brings me to my next big point, is that even within a region like where we are today, evapotranspiration rates can be different. Okay? And they can be different based off of different land covers. We'll come back to this image that is one of the first ones. If you Google image urban flooding or urban runoff, this will be the first one of the first ones you get. Okay? And it doesn't even apply to us because our forest here and across the southeast loses much more than 40%. These percents are relative to annual rainfall. Okay? So this is 40% in this cartoon of rainfall goes back to the atmosphere. And again, I'm saying around here, we're much higher than that. I would also argue that the difference between this 40% going out versus 30% is probably bigger too, and this one of the subjects of our research that we'll present here in a second. But the point is that even within a region with the same type of solar radiation, the same climate variables, the same wind, and the same relative humidity, you can lose more or less water based off your land cover. Okay? And maybe some of you have heard of urban heat islands, and a lot of times we think about those as places where there's just more solar absorption, blacktop. But a lot of the reason that we have urban heat islands is because instead of going out and running with a tank top on, you put on a big coat in the middle of summer and took a run. You are preventing yourself from perspiring. You have a given amount of solar radiation, a given amount of sunlight. It's either going to warm up the temperature or it's going to go to evaporate water. If you evaporate more water, you're going to heat up the temperature, increase the temperature to a lesser extent. So here you have a coat on, which you're going to get a lot hotter if you take a run in the summer if you don't allow your body to perspire. Here we took our coat off. We have all this green. We have water availability. Now there's other components here in terms of runoff and infiltration we'll come back to, but now we're just focused on evapotranspiration. But even within the land cover, so now let's get rid of the urban. Let's not even think about urban for now, and we're going to do that for a couple of slides. Let's just talk about out in the middle of nowhere in an intact forest. Even within that forested system, that forest land cover that we might put on a map, even within that forest land cover, there can be differences in the amount of water that goes to evapotranspiration. So if we look here, here's a full canopy. Here's a very sparse canopy. This system is just more tomato plants in the garden. Water the same amount, you're going to lose a lot more water with more tomato plants. You water the same amount with less tomato plants, more of that water is going to infiltrate into the ground. Okay? This is what has historically characterized the coastal plain. Widely spaced, uneven aged trees, maintained by frequent fire, low density, low canopy in terms of trees, right? Whereas here, this is more common these days in terms of managing forests for timber. Now, this is the goal of a lot of public land management agencies' acquisition and efforts to restore forest cover, largely for improved habitat, increased understory cover, increased habitat support for things such as the red cockaded woodpecker. Those are important functions. I would argue that over here are very important functions as well. Carbon sequestration, more timber on the ground, and of course, a very sustainable and economically important industry in terms of timber production. But the question now is, what's the difference in these systems in terms of their water use? And remember that if this system uses less water of the same incoming rainfall, then it has a higher water yield. It has more potentially groundwater recharge. And if we again take away the urban setting, the flooding setting, and the coastal setting, we go to an inland forest. The question is, can we manage forests in a way to improve or increase water supply in places that we value for groundwater recharge? We value these large forested tracts for groundwater recharge of high water quality. Okay? And it would put another feather in the cap for this type of management efforts. At the same time, forest industry is interested in this as well, not going all the way to this extreme, but is there some middle ground of managing forests and still yielding timber off of it, but maybe taking marginally productive lands because they're too far from the mill, out of production, or within stands where we're still generating timber and profit, can we do it in a more water conservative way? Increase thinning, increase understory management, those sorts of things. So again, not trying to focus on the difference between this and this necessarily, even though my next example will, and not necessarily just focused on this and not pointing our finger at forest industry, but looking at ways to manage and optimize a portfolio of functions. So this gets us to our second bullet point in that case study that I said I'd mention, which believe me, I hope, will be a nice segue to the third bullet. But now we're talking about forest management for more water. We're over here. We're not over here. We're over here. And this leads us to a project that we just finished in the state of Florida, a fairly big project called the Florida Water Yield Project. Notice the Water Yield Project is what we're calling it, where we have places where we have increased groundwater pumping, increased water withdrawals, meaning that we have less groundwater and less surface water supplies. With this question of can we manage forests, these big, large, intact forests that we already value for groundwater recharge, right, that are not necessarily adjacent to flood-prone areas, can we manage these in a way to increase water supply? Public lands, of course, because they're interested in putting, again, another feather in the cap for what they're doing on those lands. They're already doing for improved wildlife, prescribed fire, red-cockaded woodpecker. But also private industry. And actually, they came to the table. As a matter of fact, this project was actually spearheaded by some conversations with private industry to look for ways that they can yield other financial benefits from their land. Can they get some incentivization for more water conservative forest management on their land ownerships? And to ask this question, which is synthesized here in this cartoon, which is, can we relate certain forest attributes that we can easily measure on the ground, number of trees, the age of trees and leaf area, can we use those as predictor variables or ways of estimating water use or evapotranspiration, which is a lot harder to measure? And to do that, we actually did measure this, and we did it across 36 forests across Peninsula Florida that had different attributes in this green box. And we did it with a cartoon shown here with a lot of wires. Now, and groundwater wells. And I'm not going to go into the methods here, and I'm happy to talk about them afterwards, but just trust me, it was a lot of wires, it was a lot of digging. Kenyon, I don't even know how he kept track of all these wires here. You have to climb the trees. We had, it's Florida and clear cuts in some cases, so we had to have those because it got quite hot and a lot of digging, a lot of dirt, blood, sweat, and tears to get that ET term, okay, to measure that. And we measured it by saying, well, tracking the soil moisture and tracking the groundwater and how much was removed from the system through that evapotranspiration. And this is the only second graph I'll show you. Again, this is our question, and as you may have expected, the best predictor is leaf area. It's actually leaf area index, and we don't need to go into that, but you can imagine if you look up how many leaves are stacked in a system, not just one view, but how they're stacked and their total leaf area is the best predictor of ET, okay? And ET is on our y-axis, our vertical axis, and leaf area is on our x-axis, and we did a pretty good job. And we have other predictors that we can bring in about sites and tighten this relationship. But the take-home is that we can now have something that we can measure quite easily without Kenyon and all his wires and $750,000 to get at that ET flux, or that evapotranspiration flow, so that we can go out to landowners and begin to think about things such as this been thrown around in the state of Florida and beyond now. This idea is gaining traction in terms of things such as called as hydrologic easements and other things. Again, not just supporting more public land acquisition, but also private landowners to do things on their land for multiple ecosystem services, including water, and maybe ways of incentivizing those landowners to do so. And if we took the extreme, and again, I'm not saying that we can do this. We need timber, we need carbon sequestration, we need the things that are all the way on the left, but there's ways to go in the middle. But if we took this system like we're a public land agency and took it to this, well, how much water would we get out of it? Because this system is going to use less water. We can predict that with that relationship before, and we could put a number on that in terms of how much water is left over. And if we just put a number of how much, in this was funded, this project was led out of University of Florida, so I put Gainesville here because it's in the center of a lot of these sites, and present day water cost in Florida is $2.45, and of course that's an egregious probably number to put on a natural water supply source versus what you're getting from drinking water, but let's just do it for the sake of this thought experiment. You put that for per 1,000 gallons, and you took the amount of water that was made extra by this conversion, then you'd get $320 per acre per year. And you put that in the context of a hunting easement, which might be $30 to $40 per acre per year. So the role of forest, understanding how forests are different in terms of this case water use, but of course we've already talked about water storage, is important regardless of what your objective is in terms of forest management. That objective was quite different than today's objective here, which is too much water, the flip side, right? And so that gets us to our third bullet, and why most of you are here, is that is urban forest. Now we're on the right side of the screen for less water. I told you we're going to come back to this, right? Here's this forested stand, this cartoon first hit on Google image, and here's the urban system. We've already kind of talked about the difference between this, and I'd argue it's a bigger difference. First of all, I'd argue that a lot more in this region goes to the atmosphere and forested system, and I'd probably submit that there's differences in here, things that we're going to be looking at. But now we have impervious surface, more runoff, less infiltration. So it's multiple kind of changes. Most of us think about impervious surface, the water just not getting into depressional water storage, not getting that surface soil water storage that we spoke about, but also this difference in evapotranspiration, which I think is hugely important because that replenishes those storages. And so this is where we were. You have some precipitation coming in, you have some evapotranspiration going out, you have some interception, you have some infiltration, a little bit of runoff. This is what's happened throughout the world, right, where we get rid of that stuff. We imperviate the surface, we have less evapotranspiration, we have maybe the same main rainfall. Of course, that's another topic, right, in terms of changes in precipitation patterns. But we have a lot more runoff. Now, we've been going this for a little bit now, and I think we well recognize the role of urban trees, street trees I'll call them, on sidewalks and on roads where their individual tree canopies can intercept water, and the soil around those individual trees can store water. And throughout the country and in Virginia Beach, we're recognizing more and more the role of, again, what I'm calling those street trees in terms of stormwater management, improved air water quality, recreation, and all that. But what we're really focused on is the forest and bigger tracts of forest that are adjacent to flood-prone areas. And it's more than just street trees. Street trees have their own role. We're trying to talk about additional and very important role of large parcels of forest that, relatively speaking, in this city and other cities, flood-prone, and thinking about these and what they do and the various different attributes of these systems, from species composition, canopy cover, soil type, and topography. Just to remind you, and bring in this nice slide that Brian put up again, to kind of set the stage for what we're thinking about in terms of Virginia Beach, right? Kudos, hats off. A large amount of forested land is under conservation in this city, and there's still a lot of that's not under conservation, but that's still intact, right? And so we want to, again, support previous conservation efforts, but also motivate new conservation efforts. And so that gets us to the fourth bullet, which is research to inform urban forest conservation. So this is work that, again, we're a large collaborative group that I'm excited to be part of. It's really exciting to be part of actionable science, and get out of the classroom and get out of just the field with your graduate students and whatnot, but to really go to where it matters. And this specific research I'm getting ready to focus is not just me at Virginia Tech. I have colleagues in my College of Natural Resource and Environment, specifically in the Department of Geography, that are helping me lead these efforts. With two objectives. The first is quantify flood reduction services. Can we take stock of those attributes I've previously mentioned and quantify what, for the forests that we have conserved and the forests that we don't have conserved, what are their storage capacities surface and soil, and how much water they use. And really what we're trying to get at is a new tool to target conservation efforts. And that's a user-friendly web app, essentially, that practitioners can use day in, day out, this operational, that they can go to a sensitive area, a flood-prone area, determine where the water's coming from that area, and identify a forest that may, the forest cover in that particular area, and then start targeting and prioritizing, and with the targeting to get the biggest bang for your buck in terms of any kind of conservation or restoration activities. So really we need to take stock and get data for these things that we've already mentioned. That's why we thought it was important to first set the stage in terms of interactions between forest and water, regardless of context, but now in this particular context. We need to know something about surface storage, topography. We need to know something about soil storage, soil type and depth, and we need to know something about evapotranspiration, how much water do these systems use based on forest attributes. And all that, and the integration of that, the aggregation of that, determines flood reduction potential. So here's Virginia Beach. We have the LiDAR, that highly accurate remote sensing of publicly available topographic data. And we're starting to, and these are preliminary results, I do want to say, we really are just getting started, to use those data to extract, which is hard to see because we're not zoomed in, surface water storage capacity. Those colors have numbers behind them. How much water those individual depressions, those parts of the landscape can hold before they spill over, before their individual buckets spill over. Soil storage, we need to know something about soil type. That's publicly available. Plenty of soil maps out there. They're not the most precise. They're pretty coarse, but they'll do. But that's how the porosity and how much infiltration there is. But it's also the depth, right? How far usually is the water table below the surface? Well, that has a lot to do with that topography. And that has a lot to do with where the water table is. So we've taken USGS well data from the city. We've taken that topography data, and we're doing some pretty simple processing to determine water table depth across the city. But what about this one? This is where it becomes maybe challenging at first glance, because I'm not putting Kenyon out across all over Virginia Beach to measure that in the way that I've already mentioned. Lucky for us, and back to the idea about temperature, that for quite some time, we've had Landsat. It's just a satellite that goes around the Earth, shoots each individual scene about once every 8 days, and has been doing it for quite some time. And it gets a lot of things. And one of the things it gets is surface temperature. Right? I've already mentioned that if you are in a particular parcel, even this room, that the places where it's cooler, surface temperatures are cooler, they're going to be evaporating more water than the places that are warmer, because evaporating water cools that surface. If I took some thermal imagery, or I took some imagery of surface temperature of a body that just took a run with a tank top, it'll be a lot cooler than a body that took a run with a jacket on top. And that's all this is. This is the jacket. This is without jackets, right? It's cooler. They're evapotranspiring a lot more water than the red with those jackets on. And that data is available with a lot of processing. You imagine you can't have cloud cover and all of that, so there's a lot of caveats with that, but that's available, and we're in the beginning stages of stitching that data together. It's not completely stitched completely. We're missing some data here that we have to bring in, but we're starting to get good spatial data, or ET differences, annual differences in ET across the Virginia Beach area. So then the idea is to stack all that together, right? To stack it all together in a tool that can be used. And so we're, again, in the beginning stages of making this tool. Here you see the study site, the study domain. The orange is just the DEM, which is just another way of saying topographic data, right? Where you can see the areas that are the red or higher areas, and of course down here, the lower areas. But that's just to show you your study domain. Here's Great Dismal Swamp. A shout out to Chris in the back. But we can start cycling through our layers. Okay, so you see that you probably can't, but there's something about elevation, there's depressional water storage, something about water table and ET. We're going to put in soil type. We're going to put in sea level rise as well. Different layers stacked together for this particular area. We can zoom into a particular region, and this is a hypothetical case, or where we're trying to get to. But the idea is we're starting to stack that data, and at the end we're going to have a tool that says, okay, now let me put a red circle on a place that I'm interested in terms of being sensitive to flooding. Let me figure out where it gets water from, and then let me see what's in that polygon, or what's in that shape of where it gets water from. What are the depressional surface water features? There's some pretty big ones here. If we zoomed in, we could see a lot of little ones there. So that's that surface water storage kind of layer of information. Water table depth, this is incredibly hard for you guys to see, but there's some high zones here and there's really low zone here. So this, if there was some forest on there that had some good depressional water storage and was high in terms of high away from the water table, well, that would be probably a pretty good place to think about forest conservation. And then ET data. This is pretty cool. It might look blocky to you guys, but to have this type of information wall to wall across a region in terms of ET differences, where the colors light to blue mean less to more ET, are quite encouraging and very exciting to now stack that together in terms of soil water storage, surface water storage, and then how much can leave. Just my last slide. Again, excited to be part of Actionable Science, excited to be part of this working group, immensely collaborative group. Excited to be a part of. Definitely thanks to Mrs. Henley for really spearheading these efforts and being the champion of these efforts. It's a collaborative project to incorporate forests more formally into stormwater management, develop tools and information to do that effectively, to target priority areas for forest conservation, and not just forest conservation. I want to mention that these layers of information are not just in the forested stands, right? We're doing it across the whole Virginia Beach area, meaning that we're going to say something about the soil water storage, the surface water storage, and the existing evapotranspiration rates across all regions. So not just about something about the existing forest in terms of forest management and conservation, but also identifying tracts of land for reforestation, right? And also going in and managing forests in a different way to maybe amplify certain things, particularly evapotranspiration. So with that, I'll end and I'll take any questions. And again, very excited to be part of this group. Very excited to see everybody with this cold weather, even though I left snow to come here. But anyway, really appreciate being here, and thanks for your time.
Thank you so much. You know a lot. Well, we're just beginning. And I think you had some very good questions. And I think what you can see is that you can see why we have to do the science, why we have to gather the data, so that we really know the answers to these questions and all the possibilities that there might be. And so we can ask that you go home and think about these things, and when you think of some more questions and some other things that you think we should explore, let us know. I'm sure the folks in planning, Chuck Payne is around here someplace, would be glad to hear from you, or let some of us hear from you. Because, of course, this part of the project, this study is only just beginning, and we'll have some real data by early summer when we can gather again on this particular topic and get some of the numbers. But as Brian said, we don't want to be false prophets. We don't want to overpromise. But if we just know that there's got to be some value here, but in order to do the right thing, we need to have the science behind it. And so that's what we're working to do. I will say that we're also recognizing that it's been nearly a year since we had that symposium in April of last year, and it might be time to go back and look at some of those topics again and what has happened in the last year. My goodness, we had Florence and Michael, and look at what they did to us from the drainage standpoint. And so we will probably be planning another much more broad symposium in a few months. So we've still got a lot to learn, and we really appreciate your interest in coming out on a beautiful night like tonight. And somehow or other, we've managed to have storms. It's so many of these presentations. I'm not sure if this is a good idea. But anyway, we really appreciate your coming out. We appreciate the folks here at the Advanced Technology Center for accommodating us. And this will all be replayed in several different factions. I think we'll probably be seeing it on TV and YouTube and all these other places that you'll be able to look at this again, because if you're like me, you're going to need to listen to this 2 or 3 times before you can really get the full benefit of what has been said tonight. And I think we can certainly appreciate the work that these folks are doing, and appreciate Brian coming so many times here from Richmond, and thank you for making your first visit to Virginia Beach, Daniel, and we look forward to having you back real soon. And thank you all for coming.